Hi, everyone. I wanted to welcome you all to today's NEBP speaker series with Dr. Jamey Jacob, who's the Executive Director of the OSU Oklahoma Aerospace Institute for Research and Education and the Williams Chair in Energy Technology and Regents Professor of Aerospace Engineering in the School of Mechanical and Aerospace Engineering at Oklahoma State University. We're really grateful that you can be here as today's speaker, and I just wanted to ask everyone to go ahead and add to the chat where you're coming from, what team you're a part of, and I'll hand it over to Dr. Jacob.
Great. Thank you very much. I appreciate that. So obviously we're going to talk about stuff related to the eclipse. I thought I would mix it up a little bit since you've heard a lot of great discussions related to the eclipse and talk about some of the other balloon related research that we're doing kind of as a precursor before we talk about some of our eclipse measurements, basically to show a little bit about all the great stuff that you can do with high altitude atmospheric balloons that might be a little bit kind of out of what you think might be an option for doing some what we'll call soft goods or inflatable research. And so we'll just kind of jump right in. I have a lot to cover before we get to the stuff related to the eclipse at the end. Now, as mentioned, so I am a professor here at Oklahoma State University. I did my undergrad at University of Oklahoma. I always like to include a little bit of Oklahoma history because this really does tie into what we're doing with our outreach component. Now, most of you probably not familiar that Oklahoma was first a territory before it became a state, primarily made up of various Indian reservations, and most of these were various tribes for the southeastern part of the country that were forced here through a forced migration, removal from their native lands to Oklahoma, called the Trail of Tears. And so those were primarily 5 tribes in the southeastern part of the country that many of you are familiar with. But it resulted, at the end of the day, up to 39 tribes from really all across the U.S., predominantly southeastern, midwestern, but even some in the upper Midwest part of the country. And this is relevant for us because the eclipse is passing through southeastern Oklahoma through what is now known as the Choctaw Nation of Oklahoma. And so we've partnered with the Choctaw Nation as part of our outreach efforts. And so we do a lot of tribal outreach and engagement with the various tribes across the state of Oklahoma. So it's a great partnership for us. And so OSU kind of sits here, kind of outside of the tribal lands. Prior to Oklahoma becoming a state in 1907, what they call the unassigned lands, the lands that were not used for sovereign nations, were opened up in land runs. And so there is a famous land run of 1889. So there's a movie about this starring Tom Cruise and Natalie Kidman called Far and Away. And so you kind of see this in the film, and this is the land run. And as part of that land run, they had 2 groups of peoples. Those groups of peoples called boomers. No, those are not the generation that before my generation, but just to make it clear, I'm a Gen X, not a boomer. So I just want to put that out there right now. But boomers were those that went off at the sound of the cannons, which initiated the start of the land run. Essentially, everyone lined up. And those that snuck in over were called Sooners. And that's essentially where kind of our mascots for our universities come from. For Oklahoma State University, we actually use a frontier marshal named Frank Eaton, who some say is the inspiration for the novel True Grit. As a child, his father was killed by some outlaw men. He became a marshal, and then in true Western fashion ended up hunting them down, and that's where our mascot comes from. So our mascot is one of the few mascots for universities that's actually after a real life person. And then OSU mascot is Pistol Pete. And then for the University of Oklahoma, they're called the Sooners, right? And so those were the land thieves that essentially jumped the gun, so to speak, to steal plots of land before that cannon went off. Now, a little bit of my background. I joined Oklahoma State University here in 2006. I'm a professor in aerospace engineering, and my project interests are pretty diverse, related to all things related to aircraft, rockets, balloons, exploration of the Earth, and exploration of other planets across the solar system. So really focused on how we can use autonomous systems to help explore the world around us, particularly for things such as atmospheric and earth science. And so that's kind of the common thread that ties a lot of my research interests together. So as part of that, I thought I'd take this opportunity to be a little bit outside of many things that we've talked about in the NEBP seminar series to talk about solar system robotic exploration missions. It's a fascinating area of research, and then it combines a lot of different disciplines. Because if you think about exploring the solar system around us, there are only two ways to do it. One is to look at it with a telescope, and it could be in many different wavelengths, but primarily it's a remote observation using a telescope either based on Earth or an orbital telescope, such as the Hubble or James Webb. Or you have to send a robot there, and that robot could be a flyby mission, it could be an orbiter, or it could be some kind of lander or rover. And you can see all the different missions that we sent to various places across the solar system, which of course is not to scale. Most of these have gone to the moon, but of course, then we've sent a lot to both Mars, Venus, and then other planets across the solar system. And if we think about, how we tie all these elements together, what we want to be able to do ultimately is to be able to put something in there to explore both the atmosphere and things on the ground, right? If that planet has a solid surface. So maybe you want to do planetary geology, for example, or seismology or atmospheric science. And so you have the engineering team, which are building the system, working with the scientists that are essentially building the sensors that go on board the vehicle itself. Now, what you'll notice here for the kind of the exploration table, you have different systems: a flyby, an orbiter, lander, rover, flyer, or return mission. You'll notice that both Mars and Venus have had everything but rovers together. That's because Venus's atmosphere is very, very harsh. But we have put flyable systems on two of those, primarily a balloon on Venus, the Vega missions. And so that was a balloon that essentially hovered high in the atmosphere to be able to take atmospheric measurements. And then we have, of course, the Ingenuity. And I'll talk a little bit about each one of those. Now we have proposals for other systems, such as going on the moon of Titan, one of Saturn's moons, in the very, very near future. But you'll notice we have a lot of gaps in here where we haven't, been able to send specific vehicles to various planets. Now, not all vehicles make sense to send everywhere throughout the solar system. And so if we're sending something that flies, we can use this comic from XKCD to look at some good places where we might want to be able to fly various systems. So if we look, for example, the Earth, great place to fly. Venus actually has a pretty dense atmosphere and it's fairly benign at upper altitudes, very caustic and hot. It's a pressure cooker down on the ground, but you can fly at higher altitudes. Mars is actually really hard to fly in because it has a very low atmospheric density. Titan is actually a great place to fly. It's very cold, but its atmosphere is also very, very dense. And so that kind of drives whether we can actually put something on board one of these planets that we might be able to fly to do some atmospheric science. Of course, no atmosphere, not much atmospheric science, so you can still put a lander, but it'd be very difficult then to be able to put that elsewhere. So Earth, Mars, Venus, and Titan are kind of our targets, and I'll talk a little bit about some of these options then for flying these systems. Now, some of the things that kind of have in common when you think about putting systems on board are things called inflatables. And inflatables are essentially any object like a balloon that you can put in some kind of gas on the inside to be able to inflate, and then it pushes against some envelope to provide essentially your shape of that surface. So NASA has been a long proponent of developing these systems. You can see one of the Echo balloons, which is used as an early radar test here in the NASA Ames blimp hangar. You can see the size of this test balloon, which was eventually launched and flown in orbit around the Earth. So a very large system. But they've used inflatables such as airbags for some of the Martian landers, pre-Curiosity mission, the smaller rovers, or for reentry vehicles as well. And this is kind of a unique area of we'll call it engineered systems because you're fighting very harsh environments such as reentry pressures, for example, but now you have some kind of fabric or some other type of film that you have to inflate and be able to withstand high pressures and temperatures. So related to that, I'm going to talk about a couple different projects we've gone through. Now, this is kind of a survey and overview of these different systems, but I'll give you a view, and so that way at least gives you an introduction for how some of these systems might be utilized across the solar system to be able to do this exploration. So the first one is non-balloon, but it is an inflatable. This was a project we did with University of Kentucky. Professors Suzanne Smith and Sean Bailey are both part of the NEBT team doing their observations in Kentucky, I believe, this year. Now, of course, Mars aircraft. Hopefully, we're all familiar with Ingenuity, right? Very amazing feat of engineering, right? Very expensive, but it was able to achieve the first controlled flight on another planet, right? And very fantastic. Now, we have to remember that this system is purely a technology demonstrator. NASA primarily used this as a piggyback on board the mission to be able to demonstrate that flight was possible. So that way, next time around, they can hopefully include some more science experiments in this and do things such as atmospheric measurements. They were able to get some information out of the imaging system that Ingenuity had on board. So it had a camera on board that took pictures of where it was going to land at and really use that as a reconnaissance tool to help direct where the rover was going to. Now, the problem with this is, and I mentioned earlier that the atmosphere on Mars is very, very thin. It's about 1% on sea level, about what we experience here on Earth, or very similar in both density and temperature to what we see around 100,000 feet on the Earth. So very difficult to fly in. So you see this little tiny lander here requires giant propellers to be able to take off. And of course, there's no way to refuel it, so you have to be completely battery powered and use a solar panel to be able to recharge your batteries. And so you can fly for about 1.5 minutes, 2 minutes at a time, land, recharge your batteries for the rest of the day, and then you'd be able to fly the next day or the following day thereafter. But that's it. That's really all you had. So it was really just demonstrating that you could actually fly. Now, future missions really want to extend capabilities. They would really like to have a fixed wing vehicle that flies on Mars. Now, this opens up a lot of challenges in terms of how you fly the vehicle on Mars. How long can you fly for? Do you have to land to recharge your batteries, for example, using solar power? Do you have some other kind of fuel system? But one of the challenges that you have with this is, well, you have to put this in a reentry vehicle to reenter the Martian atmosphere. So how do you fold this system up to be able to make this work? So there's got to be some kind of folding mechanism for this. And so NASA has explored lots of different options. You can see the NASA Ames Kitty Hawk on the left, where it's kind of a traditional aircraft design, but folded up into a very type space. The NASA Langley Ares here, which is more of a kind of a blended wing body or flying wing design with a tail in the back, and how it is completely folded up. And there's a NASA ERC Marius system here or Mara system, right? Again, the wing is folded in and then somehow that fits back into the reentry pod. And you can see a little bit of a better idea about this as well. Now, this picture also illustrates another important soft good design on here, which is the parachute and the supersonic parachute design. Really important component. The parachute doesn't work on any of your Mars reentry vehicles, then your mission will fail. So designing this parachute was a big challenge for the NASA engineers. They did a lot of testing in the wind tunnels. And if you look at the NOVA that they produced several years ago on the NASA mission. They have some great shots and a short discussion of the development of the supersonic parachute as well. But essentially, this aircraft like this has to fold up in a really, really small space. Now, one thing that NASA has examined over the years are inflatable wings. And you can really think about this as essentially some type of inflatable pool floaty. But now you're doing this in the shape of an aerodynamic surface. You're compacting it, you're stowing it, and then you're inflating it using some either compressed air or chemical reaction for the mission to be able to deploy the wings on command when you're ready to fly. And this is an example of one of the NASA tests they did at the Dryden Flight Research about 2 decades ago. Now, here are a couple of the tests, and I'll show the videos from here. And you can see this is the NASA Ares mission on the left. So this is from a high altitude balloon. So they're using a balloon to do this test. That's another valid use of a high altitude engineered balloon system as a tool, is to deploy these systems up to high altitude so that way they can test in a relevant environment. They're not testing on Mars, but they're testing in a Mars-like atmosphere. Because if you can fly at about 120,000 feet, you should be able to fly on Mars. So you can see how once it got up to a certain altitude, it unfolded its wings, it then deployed, and then it starts flying back down in the atmosphere. So this was the NASA test that they did to demonstrate this. So our student team, working with ILC Dover, a company that's built a lot of the spacesuits and Martian airbags for NASA over the many years, built and tested an inflatable wing. And so you can see, again, this going up on a balloon and primarily showing the deployment of the wing during its actual flight. You can see some integrated solar cells here as well. And this was primarily to demonstrate, yes, we could deploy this system under a relevant environment and that the wings would actually work. And then we did a lot of other flight tests related to that. So as part of this now, what we've primarily been focused on is looking at, well, now how do you integrate this into an aircraft concept? So we've taken the Mars Electric Flyer design, which is a very simple UAV concept developed by scientists at NASA Langley, and you can see it's an electric twin rotor aircraft that's designed to essentially take off and land much like the Ingenuity is designed to, but that will actually tilt forward so it can fly for much, much longer distances now because it uses aerodynamic lift instead of powered lift. So our students designed an inflatable wing. These were actually a team of high school students that we had working on this as part of our summer project. So they built the wing, integrated it in, and then went out and did flight testing with it to demonstrate that it could actually fly. So this was kind of the end of the project and showed that we had an actual demonstration concept that would work from this. And from here, we're able to move to the next steps, which is evaluating, the engineering of the system, how do you pack it, and how you actually get the system to operate. We kind of ended the experiment strapping this to one of our high school student volunteers, and then we were able to fly them around the adjacent soccer field. Okay, and no, that's actually a styrofoam dummy. One, it's not powerful enough to lift the weight of a full student. And they also frown on that if we go flying students around the back without some kind of safety checkout first. So that's down the road at some point. Okay, next, we'll kind of move more into the ballooning side, right? So we're going to talk about a project called P-STAR, which is Planetary Science and Technology through Analog Research. And this was a project that we did joint with NASA's Jet Propulsion Laboratory and Sandia National Laboratory. And this was originally came out of a talk I went to at AGU, American Geophysical Union, where hopefully many of you will be going to at some point in the future, presenting some of your research related to the eclipse. And purely just kind of one of those talks that I thought, well, this looks interesting. Walked into it, saw what they're doing, and said, well, we got to get on this and connect with them. And that was from Dr. Danny Bowman at Sandia National Laboratories in terms of its design of solar balloons. Now, that was purely for Earth atmospheric research, but then JPL thought, well, this might be an interesting opportunity to explore balloons for Venus. Now, why do we want to fly on Venus? Well, while Mars is a very different planet in terms of its historical evolution, Venus appears to be the closest a similar terrestrial planet that we have to Earth. Similar in size, similar composition, but obviously different in its orbital location. However, its atmosphere, its dynamics, due to the fact that it's essentially tidally locked, has a very weak magnetic field, is very, very different. It has a runaway greenhouse effect. So from a scientific standpoint, this is great to study because it's a potential worst case scenario, right, for where Earth might be headed in the future. So understanding Venus and its dynamics is really important to understanding more about the Earth itself. Now, there have been landers in the past. This is a picture from Venera 13, one of the few photos that we actually have from the surface of Venus. Looks like you're somewhere in Arizona, for example, or somewhere else in the desert. Only difference is this is about, 700 degrees, give or take, and about 90 atmospheres worth of pressure. So you're quite literally in a pressure cooker. And add on top of that, if the temperature and pressure weren't bad enough, the atmosphere is also laden with sulfur dioxide. So you have a triple whammy. And it makes it very difficult from a engineered approach because you have to design the system to be able to withstand these very high temperatures and pressures, plus the caustic environment itself. So very, very difficult to do. And you can see the plot here, right, of what we have in terms of the atmosphere. Think about how you relate this. Hopefully everyone now is very familiar with the Earth's atmospheric profile in terms of temperature as a function of altitude. Um, but you'll notice that it follows kind of a similar profile to Earth. It's just very skewed to very, very high temperatures at the lower altitude itself. Now, if you put on top of this Earth's temperature profile, you'll see that there is actually a crossover point where Earth and Venus are very similar, both in terms of pressure. This is about 1 atmosphere pressure on Venus at this higher altitude, and very similar in temperature. So this is actually a really kind of safe place to study, and that's where NASA's balloon concepts come into play. This is a great report by the NASA JPL team, Aerial Platforms for the Scientific Exploration of Venus. And you'll see that they go through a lot of different concepts, which include both balloons, fixed-wing vehicles, other types of airships as well. Now, our part on this project is really to look at NASA's concept of how we use a balloon for airborne atmospheric science above the cloud decks. And you can think about this thing floating around Venus. Maybe you have the capability to drop a probe down into the clouds. Maybe you have some other smaller probes that you drop that can probe the atmosphere and send information back to your balloon, which you can then send back to Earth. So this is the basic concept that we're using now as a way to explore the atmosphere of Venus. Primarily the difference is, well, you drift with the wind, you don't really control where it goes. Now, in particular, the JPL team that we're working with are interested in doing seismology on Venus. They want to know why Venus's interior is so different from that of the Earth. It doesn't appear to have the same dynamics in terms of that interior structure of the planet that we have here on Earth, which results in very different type of behavior. But they do theorize that there are not what we call earthquakes, but Venus quakes. And so they want to be able to study the seismology. Well, how do you study seismology if you can't actually put a seismometer on the ground? That's how we measure earthquakes on the Earth now, is we essentially have an accelerometer we attach to the Earth's surface. When we have an earthquake and the ground shakes up and down or back and forth, we're able to measure that and then turn that into an earthquake reading. One theory about how to do that is you use this thing called infrasound, which is the low frequency sound below the threshold of human hearing. So if you could pick that up with a microphone or an infrasonic sensor that's on board your balloon, then you could determine both range and bearing of where that epicenter of the earthquake is at. And that's exactly what we've been doing, putting infrasonic sensors on board these balloons. So I won't get into too much detail about that piece. There's some AGU talks out there that you could look at. to delve into that more from some of our students and partners at JPL and NASA. I'm going to talk about the balloons. One aspect of this is we're using a different kind of balloon technology, primarily because we want the balloons to be relatively inexpensive, so we don't have to worry about all the helium, but also we want them to float for very long periods of time and be very, very quiet, because that quiet nature of the balloon allows the microphones to be able to pick up those infrasonic signals that we're getting from the seismic waves, the P waves and F waves that we're getting from the shaking of the Earth. So we're testing that here on Earth to know that will work later on Venus. So this kind of gives you an example of what these balloons look like. This is actually construction. We quite literally use plastic painter's sheeting that you can buy at any hardware store, and cut that out into gores, tape that together using clear construction tape, and then we darken it using charcoal. And I'll talk about why we do that in a minute. And that is our balloon. Very inexpensive to put together, very, very easy, right? And so it's while typically not reusable, it is great for one-off systems. Now, there are two ways we go about flying these. One is using the system called ground inflation, where we essentially air the balloon up. And because of that, well, where do we get our buoyant lift from? Well, what we do is we darken it using essentially charcoal to give it basically a light kind of gray color. That dark material absorbs the solar infrared radiation that we're getting from the sun, heats up the interior, and now we have buoyant lift. So it's essentially a hot air balloon, but instead of using some propane gas to heat your air, you're now using the power of the sun. And the theory behind this is, well, you're essentially getting free lift. So you don't have to worry about anything but essentially darkening the balloon. Now, for some of the high altitude testing, we've also used a technique that Dr. Bowman coined as Grand Slam, where you're using a balloon to lift it above. Let's say, for example, you're trying to launch on a cloudy day. Well, in that case, you want to do a Grand Slam launch because you can't get the solar radiation to be able to heat the balloon up in the morning. You can see some examples of various Grand Slam tests that the team did as part of this throughout the campaign that they ran to measure earthquakes a couple summers ago. So I'll show a quick video of this just so you can get kind of a sense of what these look like. And you'll notice there are quite a few of us. This is I believe this is a 10-meter diameter balloon, but it might be a 7 or a 9. I don't remember exactly, but you'll notice the tension of the line and how this is rigged here. It's acting like an aerodynamic cell in this case, and that's why it looks like it's caving in on one side, because the wind is trying to push it. And we're just walking it until it gets enough lift. And I'll pull it over here, and you can see what it looks like as it goes up in the air, right about here. Let it go, and it starts to lift up, and then it starts to take on that kind of traditional balloon shape as it starts to inflate the envelope. And eventually, when it gets up in the air, it'll look a lot like this and really start to fill completely out. Now, typically what we do now, this was actually a flexible opening. We've actually changed the design such that we use a hula hoop right in that center to be able to keep that rigid mount fixed. Now, this other piece I'm going to show is actually a video from Sandia National Labs. So you'll see what this looks like as this is going up. So here is a Grand Slam launch. So this was the test of one of the Grand Slam tests that did. This is Dr. Danny Bowman. There's a helium balloon, the solar balloon, and then the parachute lifting up the payload, which has the camera on it. And the idea is this gets to higher and higher altitude. Eventually the balloon will burst. And then as the solar balloon starts to drop down to the atmosphere, it ram air inflates. So air is forced into it. And you can actually see it will breathe quite a bit. The air will come in and out. But up at this higher altitude here, you can see that it's mostly deflated. Now, pretty soon, the balloon here will reach its limit. And just like all of our weather balloons that we've been launching as part of the Eclipse campaign, it will burst once it reaches that altitude limit. And once it bursts, of course, it loses that buoyant lift and falls back down. Now, I love this piece here. We'll come back and play it here again. Slowly, you can see the balloon bursting and how it retains that spherical shape. and that light shadow of that powder that you have that we're all familiar with the balloon as it bursts. Now, as the solar balloon starts to fall down, ram air inflated into the balloon itself to inflate the envelope, and then it heats up using the sun. And then after that, it will float for the rest of the day. And you can actually see the picture here of that ram air inflation process with this balloon looking up. Now, a typical profile from a solar balloon is very different than what we see with a typical weather balloon. You can see a ground launch here in balloon. It rises much slower than we typically have with a weather balloon, which will have a fairly rapid ascent rate. This is a grand slam launch right here, which again is very similar to a traditional weather balloon launch that we have. Now, one of the things you'll notice on here is you do see our solar balloon has a couple different sensors separated. So we have two sensors on the balloon. Why? Is so that way, as that sound wave, which is traveling obviously at the speed of sound, hits the balloon, we'll have a short time lag separated by enough distance that based upon our sampling rate that we have, that we can determine the time difference between those two, and help use that for range and bearing on the actual source itself. Now, we have been successful in detecting ground systems, both earthquakes. I'm actually showing these are actually blasts from the McAllister ammunition plant here. So you can see as we're flying over, in this case, we're picking stuff up from the ground down here. And so we're actually able to trigger that. We have successfully gone down to an earthquake as low as magnitude 2.7. So this was demonstrated to be successful. Now is moving on to the next phase at JPL in terms of, well, how do you now engineer the system for potential flight on Mars in the future? Now, one of the big differences with these balloons versus what we do with other balloons is we have to recover these payloads. One, because the sensors are very expensive. We'd like to get them back and reuse them, but also we're storing lots and lots of data on board. So we spend a lot of time going out and recovering them. And you can see some of our students here, particularly Zach and Emily on the left and middle respectively, going out and recovering these balloons in the field. And for those of you who've done any type of balloon recovery in the past, balloons have a penchant for essentially finding the most onerous place to land. And so if they can land in water, they will. If they can land in the highest tree, they will as well. And so recovery tends to be quite an adventure, but we have nearly 100% successful payload recovery. We have one payload that is somewhere in northern Texas that's still stuck in a tree that we could not get down. So out of about 100 or so payloads that we've launched, we've recovered almost all of them except for that one. Now, our final balloon discussion is actually going to be on using the solar balloons for more observations. So rather than observing what's happening in the ground, however, we're going to use that same system to observe a reentry vehicle. So as you can see right here. Now, this would be interesting from a number of applications. One, meteorite. So you could have a balloon that's flying an infrasonic payload. A meteorite or a meteor is entering the Earth's atmosphere. It's generating a shock wave, and through that shock wave, you can then determine both where that meteor is entering at, as well as the size of the meteor. Problem is, you also need some way to test this. Now, you can think of other things that could detect. For example, reentry vehicles. It could be something like, a manned capsule like Orion or Dragon, or some other satellite that's reentering, or maybe it could be a missile that's coming in through the atmosphere. So we used as a target of opportunity OSIRIS-REx. So for those of you familiar, OSIRIS-REx was, again, a NASA experiment to recover a sample from an asteroid, primarily Bennu. So we have this asteroid, which is in a near-Earth orbit here, and so OSIRIS-REx was launched with the whole goal of rendezvousing with the asteroid and recovering a sample. So you can see OSIRIS-REx there, and we'll have a short video here of the actual process. So what you'll notice, here's OSIRIS-REx. These are actual images from the probe itself as it's going in towards the asteroid. It's going to deploy a probe, essentially an arm. So this is not actual video, this is simulation, but now you can see the actual video. runs in, it basically touches, and then through that process of impact, shoots up a lot of rock and dust, at which point it grabs that sample and stores it in a container. And as always, if you have a successful mission, hopefully you'll be doing this on Eclipse Day as well. All excited that you saw the eclipse and you're getting great data from your balloon. So you should certainly celebrate. Now, after this happens, we have to get the sample back for analysis. So this returns to Earth. Now, what's unique about this is we know all the characteristics. It has a trajectory very similar to what we'll have with asteroids entering Earth's sphere of influence. And so we can use this as a great model to help determine if this is going to be a way to measure these observations. And we know everything about this. We know the reentry angle, we know the mass of the vehicle, we know the ballistic coefficient, or the ballistic parameters. So we can use this as a great test in order to be able to calibrate our system. So we launched balloons, and so that way we'd have balloons in the air with these infrasonic sensors performing these observations as the capsule was re-entering. And so you can see the capsule here after it landed in the desert, along with some of these samples as well. Now, we thought NASA would be all excited about this and say, hey, we're going to fly balloons and use this as an opportunity to get some other science. And they're just like, don't mess with our reentry vehicle. As long as you don't mess with that, we're good. So do your thing. And so we had, again, our team go out. We actually had a set of both ground experiments as well as balloon experiments. I'm just showing the balloon experiments here. Since these were early in the morning, based upon the time of day that the capsule was re-entering the Earth's atmosphere, it meant that we had to go through the process of doing these grand slam launches with the balloons to get them up in the air. We actually did run through some tests of try to do some early morning tests or even some night tests to see if we get these things up and get them to float. But they really do require that sun's energy to be able to make them happen. So in this case, we use traditional zero pressure balloons to be able to lift the systems up into the air. And there goes payload number 1. And you can see another weather balloon over there, and then payload number 2, and you can see the sun coming up over the horizon. But also very successful, able to get the signals measured from the balloon systems, and they're still going through the data analysis process now as part of that. Okay, now one final thing is kind of another application of using these inflatables or balloons is a project called Hop, Skip, and Jump, done with a company called Global Aerospace Corporation as part of a NASA JPL and NIAC project. And this was a really completely different application. So this was utilizing data from the New Horizons mission. So New Horizons, of course, was a probe meant to really focus on Pluto and similar objects. Now, what you'll notice here, it uses Jupiter for a gravity assist maneuver, and we do that primarily to reduce the total mass of the spacecraft by saving fuel. And that last maneuver then allowed us to intercept Pluto. And of course, it went on and looked at some Kuiper Belt objects as well. And so out there taking great data. Now, it was a flyby. If you go back and think about those experiments, why are we sending this thing all the way out to Pluto, but not using it as an orbiter or a lander? Well, again, it costs a lot of money because of the fuel it has to carry along with it. So a flyby is really about all you could afford in this case for the first experiment that you're doing or first observation that you have of Pluto. Now, one of the interesting things that it discovered that Pluto, even though it's about the size of the Earth's moon, actually has a very, very large, albeit thin, atmosphere. And you can see this is actually an image of Pluto looking back towards the sun, right, towards the center of the solar system, and showing that, there's actually an atmosphere there that is dense enough that it's visible using that sun's shadow or that refraction that you have coming from the sun. And this was a surprise that they didn't expect to see this. And so if you actually do a comparison, Pluto, again, about the same size as the moon, and we know the moon doesn't have an atmosphere. But we'll see that the extent of the atmosphere goes all the way out, such that the atmosphere itself is larger than the Earth's atmosphere. So it's actually a very extensive atmosphere, just very, very thin. Well, the idea then was, well, if we can use, like we have here on Earth, the Earth's atmosphere as a way to decelerate spacecraft, maybe we could do the same thing with Pluto and use Pluto's atmosphere to do that. So what we do is develop essentially a giant balloon that would deploy as you have your spacecraft approaching Pluto. And this very large balloon would then use the drag created from the friction that you have with Pluto's thin atmosphere to decelerate and land something on Pluto. So this would be a way of keeping your mission very light and thus affordable, but having essentially your cake and eating it too. You can now use this to decelerate and put a lander on Pluto, where ordinarily you would have to have some very large deceleration system in order to be able to decelerate to Pluto. So this is called an inflated enveloping aerodynamic decelerator, or EAD. Large envelope. You can see the tiny little lander right here down at the bottom. So this is very similar, going all the way back to the original, the first part of the talk we had, about the similar size to that NASA Echo balloon, right? So, which was developed all the way back in the late 50s to, test radar on Earth. And you can see the inflation of the balloon here starts off very, very small, inflates and becomes this fully inflated reflective object in Earth's atmosphere. So it's using similar concept. Now, there's more of an engineering challenge here, however, because we're actually using this to help decelerate the spacecraft. So because of that, it has both high temperatures as well as stresses. They're actually acting on that envelope itself. So a number of simulations were run so that we can look at as it's going through that reentry phase, reentering Pluto's atmosphere, that you end up with high stagnation temperatures that heat up the envelope as well as stresses. So we had to ensure that we could actually design something. You can see it has a lot of load lines attached to the payload that help distribute that aerodynamic drag or load that you're getting around the envelope of the balloon itself. And these were our scale models that we developed as part of the project. You can see very similar type of construction technology. We were leveraging that expertise that we had developed with developing the solar balloons in terms of developing this overall gas bag that we had with the system. Now, it's like, what does this have to do with eclipses? I thought I was going to hear about eclipses and drones. Well, that's our final topic of today then, is to bring this all the way back to NEBP. Well, what we're doing, so we've been involved in several different eclipses. We started in 2017 in Nebraska. That was our first, and you can see our short video there. So this is with the University of Nebraska team, as well as the National Severe Storms Lab. And you'll see we're operating balloons or balloons in the back. There are drones off to the left, and then we have lots of ground stations as well. So this is prior to the NEB project, so we were out primarily doing these observations on our own, but did some coordinating with some other NOAA teams and university teams across the country, including our University of Kentucky partners. Okay, so you see the eclipse pass through. So that was kind of our first foray into atmospheric science. Now, we did use drones in this first one to probe the atmosphere and take some initial measurements. Now, we were part of the Chile campaign in 2020. I'm not going to talk about that one. You can see our picture here from our Chile team that we have down here. Jen Fowler gave a great discussion of that. So I'm going to encourage you that if you'd like to learn more about what we did in Chile, the atmospheric river that we encountered, and kind of the lack of the eclipse. We only got to see a thin sliver of it, which you can see right here. That was about the best eclipse picture that we got for that day. But we still got lots of great data that we could do good science with. And again, that's what we're here for, and that's what we were focused on. And then finally, the annular eclipse back in New Mexico, which again, everyone is familiar with. Now, I'll kind of go back and reemphasize why we're doing this. I know everyone knows this already, but if we look at that atmospheric boundary layer, right, where we have the basic ground, we have sunrise, the sun starts to heat the ground up, we get lots of buoyant air moving up through the atmosphere starts to mix. That's the stuff that we really want to study. And of course, what happens during an eclipse is we're turning that solar forcing factor off. We no longer have that energy that's heating the ground up going into the atmosphere itself. And what we theorize, of course, is that, well, that's a way to generate atmospheric gravity waves. And those are the things that we're trying to measure with the actual balloon itself, and then turn that back into better models for improved forecasting of both weather and climate. Now, what we're going to be doing is a little bit different, is in addition to the weather balloons, we'll also be flying a solar balloon or two, as well as doing some drone observations. So this gives us a coupled observation that we have with the eclipse. Now, the one I'm going to focus on is just Nebraska, since Jen talked about Chile, both in 2019 and 2020, in her talk last week. So it gives us an opportunity just to talk about this particular event. So you can see a couple of our deployment sites. These were of our partners that we had. This was our site here. So OSU, University of Nebraska in the National Severe Storms Lab. We had the Kentucky team right here. There was a NOAA site here. And then we're comparing with data at the DOE ARM Southern Great Plains site in northern Oklahoma. And this was kind of our local zoomed in picture of the eclipse right here. Okay, and this was our particular site. Now, I won't go into details. We did have some convection, and you'll see that in kind of the images that we showed earlier, and at least anecdotal evidence that the eclipse did have an impact on the immediate weather dynamics around us, that there was a reduced amount of convection as the eclipse passed through, okay, which again is great data. Now, play through this video again. You can see kind of how we time this with our ops. I like to emphasize this. Con ops is really important. Who's doing what when, right? You have to know what mission that you're in charge of, how long it's going to take to prep your pieces, you know, and mostly, again, balloons and the ground control stations. But if you're doing other observations, you want to be able to time all that in. You see we have the eclipse pass through. Our auto lights automatically turn on, right? Something to think about, you know, it's like, hey, should I turn the auto off on your lights? And then back to normal everyday weather. Now, I'll show a couple of the data from this just so you can see this real quickly. So our ground station, both solar radiation and temperature, you can see the solar radiation, and obviously evidence of lots of cloud activity, right? We have clouds passing through, which is dropping this radiation down from what should be, you know, it's a theoretical maximum that we'd intend to get if it was a nice clear day. So lots of cloud cover, things start to clear out, then the eclipse passes through, drops down to near zero, and then rebounds pretty quickly after. And actually, you can notice here that our skies are actually pretty clear here because it's actually rebounding pretty quickly in a pretty sinusoidal fashion, working its way back up to its maximum. And of course, the temperature is lagging, but correlated very strongly with this. Now, we also did a lot of balloon soundings. I kind of like to show this because these are all the balloon soundings just stacked on top of one another, kind of going throughout the day as part of this. And so these were clustered, a little bit different from what we're doing in our project here, in that we had a whole lot of balloon soundings that we're doing in a very short period of time. So we only started in the morning and then worked, you know, until immediately after the eclipse had finished, so we could see the rebound of the atmosphere. There are evidence of waves in here that you see traversing, which if you now put these into a contour plot, you can see the evidence of as you see the rebound of this atmosphere and this wavy motion working its way through. Now, there are obviously going to be more tools that the teams will be using here in terms of the wave analysis to be able to pull this data out, but this is a nice visual representation of it to be able to see first that impact of that reduced insolation, the rebound in the atmosphere, and kind of this wavy behavior that's happening later in the day. And this is, keep in mind, fairly low ABL response, right? This is, you know, we're looking for stuff both in the ABL as well as the upper atmosphere in terms of that behavior. Now, I'll kind of finish this off looking at the satellite observation. This is what GOES 16 picks up as it's working its way through across the continental US. And you can see our radar down here. And so this is a radar loop. And as this is coming through, you'll notice this convection. And we have our eclipse happen about right now. And then you can see kind of that convection start to really dissipate very, very quickly. And you can see that in the video to the southeast down here. Focus on the eclipse up near the top of the image. You can see the moon passes through. We have the eclipse. See some of our drone flights going up and down. and then that convection really kind of dissipates off to the south east of us as well. Okay. So I'll finish this up with just a quick video showing the annular eclipse. I like to show this one since many of you were involved in it. Hopefully you've already seen this, but I love this shot that even though it was an annular eclipse, you can really see the effect of this as it passes across the daylight surface of the Earth. And what's unique about this, it does have this kind of eerie red glow that you get from the annular eclipse that you don't tend to see in the total eclipse. So it's a very different experience, right? So hopefully you'll get to experience the total eclipse in the same glory that you got to see the annular eclipse in. Okay. Now, this is what we hope to see on April 8th, 2024 in Broken Bow. We're crossing our fingers for great skies. This is one of the pictures that we got from August 21st in 2017 in Nebraska. And again, I would say a life-changing experience for all of those who are able to witness it firsthand. So with that, I'd be happy to take any questions if there are any.
We did have one question in the chat that was asked, or sorry, that was asked beforehand. And it was if you could expand on how balloon data helps fill out ongoing atmospheric data research that has been completed by drones.
Yeah, so they're really different tools, and typically when we're using drones, we're using those to help augment what we're getting off of balloons. Yeah, this is some of our ongoing research that we've been using, small, what we call them UAS or drones to be able to supplement profile. And we're doing that, or profiling, we're doing that right now with the National Weather Service on a NOAA project to help fill some of those gaps. And one of the advantages of UAS are they're more controllable. You control what their ascent rate is, you control where they're going. Balloons drift with the wind. A drone you can have stay in the same location, go straight up and down, and you get it back at the end of the day. So you can reuse it, swap out the batteries, and you can fly again. The downsides are, one, they don't go as high as obviously, right? So you can't fly them up to, several thousand, meters typically, particularly here in the U.S. We did do a flight test 2 weeks ago with a system over in Europe and able to get it up to 18,000 feet, which is still pretty high. Not as high as we'd like to get with the data, right? We'd really like to get up into the 30,000 and 40,000 foot level to be able to get some of that higher upper level data as well, where we expect some of those waves to be at. But it's a good kind of gap filler and particularly great for pulling some of that data in the lower ABL that, your balloons may pass very quickly through. So you can end up with higher resolution data. And I should say, I'll throw one last picture up here. This is one of our research faculty, Dr. Ben Lowe, with some of the other drone systems. This is a very kind of similar analog to Ingenuity. We also do a lot of kite research, and one of the NASA scientists that we'll have with us on the Eclipse Day, Jeff Bland, who came and gave a presentation some weeks ago on kite measurements as well. So we'll also have kites as part of our experiment. So we'll include balloons, drones, and kites all together to be able to do, hopefully, a really great sampling of the atmosphere on that day.
In case you're not monitoring the chat, Bill from Central Wyoming College said, I really think the solar balloons are an interesting concept as how we look at how we can continue ballooning with our students after this coming eclipse.
Yeah, and I'd encourage you, if you're interested, we've got some good how-to guides on how to build solar balloons. Again, it's very simple, very inexpensive. It takes kind of a little bit of practice to be able to get them up in the air, but once you've learned how to do it, it's a really great tool, and I love it just from a kind of a natural atmospheric science aspect, because you're literally seeing a parcel of warm air as it forms and captured by that envelope and moving up through the atmosphere. So once they get airborne, they're very graceful to watch as they slowly drift up through the atmosphere.
If anyone has any last questions, they can put something in the chat or unmute themselves. Otherwise, I'm going to link the speaker series feedback form in the chat. If you have any comments or things you would like to see in the future, feel free to share your thoughts there. And then we will not be having a speaker series next week, but we will have one on Tuesday, March 26th at 10 a.m. Pacific Standard Time. And if that's it, I'd just like to extend a big thank you to Dr. Jamey Jacob for taking the time to present. And thank you all for coming.
Thank you so much. Thanks for the opportunity.